I'm not sure, but I was thinking like maybe complement of uh, win zero safety, or if player one is playing, then complement of win zero, like of the safety game.
Okay, win. So, okay, so this sphere. Okay, so let us record this first, repeated reachability. And first we are just seeing some, yeah, if there is some methods which we can use on our own. So you are saying win zero of,
Uh, the safety game.
okay, with what being the safety set?
T.
Okay, safety set being,
And then we take the complement of this. So I was thinking maybe this would work.
uh, so these are the vertices. Hmm. So here, are you saying player zero is playing to win? Okay, I mean,
Yeah, but again, this doesn't encode that infinitely many times. So like
right.
that condition is not there.
Okay, that is fine. But what I just want to understand is how does it, like, does it have, some things in, yeah. So let us say this is safety and T are the safety vertices. Okay, so maybe G is the graph and T are the set of safety vertices. So, um, so these will be the vertices such that player zero, yeah, the way we have used the notation, this is, yeah, okay. So these will be the vertices such that player zero can ensure that the game doesn't always remain in T, right? So if you
Yes.
rather take this, which is probably what you were saying, take the complement, win one, because when we say a
Yeah.
safety game, then win one means player one wants to remain in that safe set and player zero wants to avoid. Yeah, so certainly, yeah, certainly this is inside, let's say, repeated reachability of G. Okay, or maybe win one of repeated reachability. Win one of repeated reachability game with G as the input graph and T as the target set. These two both have to go in as inputs. Yes, this will be in it, but this may not be all the vertices. As you can understand, you can easily just make a counter example.
Yeah.
Yeah, some sort of cycle in and out of T. Yeah. So how do you find out all the vertices? Yeah. So in fact, what we will do is we will do this rather indirectly. We will do this a little indirectly. Okay. Yeah. So can you tell me, yeah. So maybe I can ask the question like this. Can you tell me some obvious vertices? You have told me some obvious vertices which are in Win1G, right? In Win1 of repeated reachability of G. But now, can you tell me some obvious vertices which are not in? This will be good for us to know. In terms of what we have studied so far, right? In terms of what we have studied so far. Yeah. So you will notice this, let's see if you agree with this. Complement of Win1 of only reachability. Maybe I can just write Win0, but let me just write it like this. This is certainly in the complement. Yeah, so I'm just being stupid. I should first just say like this. right? Well, let's just parse this. So those vertices from which you can go in T infinitely often are certainly contained in those vertices from which you can go in T at least once.
At least once, yeah,
Right? So
yeah.
this is our like obvious statement. So then we take the complement of this, right? So that is, that then it will become the opposite.
So we're kind of looking for sets of which win1 RR is a subset or a superset.
Subset. Uh,
Yes.
e-
So like in the first one,
both.
uh,
Yeah.
we get that win1 RR is a superset of win1 safety. Second one, we get that it's a subset. So like we're sort of looking for that sort of relationship.
Yes, like it's a subset of something. And what we are kind of looking for, I would say, is that we want to know for sure what vertices are not in win1G, win1 RR, okay, so that we can delete those vertices and play the game on the smaller graph. Okay, like those vertices which are not in if we can get hold of some vertices which are, we know that they are certainly not in win1 RR. Okay, then we will remove those vertices. Obviously there needs to be something more, but the idea is that we will remove those vertices because they are not in win1 RR, so we will remove them and play the game on the smaller graph for win1 RR. Okay, we'll play for
Yes,
player one to
yes.
win for this game, but on a smaller graph. That's why we want to know for sure which vertices to omit. Okay, that's why we are first engulfing this into this, so that if we look at the complement, then those we can maybe omit. Okay, so yeah, so maybe then I will not write this. I will not write this. Yeah, what I will then say is that um, you look at V minus win 1 R G comma T, right? So this let us say that this is this green thing. Okay, it certainly doesn't contain T, right? This doesn't contain T because T is in win1 RGT, G comma T, right?
Like it's a target graph, so any vertex there would like it would automatically
Yes,
be
in T,
yes.
so it will be in win1 RGT, right? So now we look at these vertices, but yeah, so these vertices are certainly not in win1 RR. Okay, but what is also important is if the game goes in this vertex, if the token goes in this set, then player 0 can ensure that it remains in this set, because it's a safety. It's safety for player 0,
Yeah.
right?
Yes, sir.
And that was even in the algorithm when we did win1 reach, and that's the very definition, right? You cannot reach win1. So yeah, right, means that if you are in this, then you cannot reach T, which means you cannot reach here even, because if you can reach in win1 RGT, then you can reach T after some time. So it basically means that if you are in this complement set, then it's a closed set. Player 0 can ensure the game will remain there. Okay, that is important for us. I will write the algorithm, but that is important for us because that means if you are playing the game on a smaller graph, okay, then the game should never interact with this part of the graph. Okay, which will roughly ensure that if you are starting whatever winning vertices you find for player 1 for this game on the smaller graph will be winning. Okay, and no other vertex will be winning, so you'll not miss out on anything. Okay, yeah, it's a little, but if it will come to it. But now what we have to do is we have to look at, let us say that we look at this set. So what should we call this set? Let me just see what they call it in the book. I will call them reach one complement. Right, so they just call it reach one complement, but they have a nice notation which we should know. Yeah, let's just call this W naught. Okay, or also calling it W naught prime, otherwise it will be confusion. Yeah, so we take W naught prime. Okay, let's call this W naught prime. It is also important to consider not just this complement, but also those vertices from which player 0 can reach this set after finitely many steps. Okay, so think of this W naught prime as your new target set. Okay, now if there is some vertex which is not in W naught prime, but player 0 can reach T prime, but player 0 can reach this target set, then also those vertices cannot be winning for player 1 in
Yeah,
repeat. Yeah,
we'll have to delete those as well.
yes, right, because you see, because sometimes it may reach T, but eventually player 0 can take the game in T prime, and after that he will not let the game go out of it. So it will be reach, he will reach, but it won't be repeated reachability for player 1, right? So we will take those also, we will take those out, as you say, so we delete them. So that the notation should be that now we play the reachability game, but player 0 will be winning. Just a minute. Or is it that one? Yeah, that's fine, right? Yeah. So now we play reachability, and again, let me look at what's the notation. No, there is no notation. Yeah. So now we play the reachability game, or okay. So let me write this. But we have usually used this notation for this. This is winning for player 0. The player 0 wants to reach there for reachability, and the set is W naught prime. Target set is W naught prime. Yeah. So here player 0 wants to reach this W naught prime. Okay, this should not be seen as player 0 wants to avoid W naught prime. Yeah, obviously that will not be the case. Player 0 wants to reach W naught prime. Yeah, but those are the vertices we'll remove. Okay, now it's easy. Okay, now we will look at, let me just shrink this a little bit. I want to just do this on this page only. Oh, yeah. All right, this is good enough. Yeah. Now what we do, we take this new graph. We take a new graph, okay, which was the original graph, but we remove these vertices. Okay, we remove these vertices, and whatever algorithm, so so then we just find win 1 RR on G prime for this target set T. Right, we find this set. Okay, we compute this. See, this is going to be a smaller graph. Okay, Right? So let us see once again. So we set out to find this, okay, but we got a smaller graph, except in one case it will not be a smaller graph, and we can think about that case separately. That will actually be an easy case. And in general, you'll get a smaller graph, okay, and then you try to find win1 RR in this smaller graph. For this, again, actually, you can go to a smaller graph. And if you don't go to a smaller graph, then what happens? That case you can deal with once and for all. And otherwise, you go to a smaller graph and find there. And to find here, you go to another smaller graph and find there. And like this. So it will end infinitely many steps. Is it any good? Understand it?
Yes, sir. I understood.
Kind of, yeah.
Yeah.
Okay,
Like we got a small graph
right.
because we've removed everything that's in read 0 W naught prime.
Exactly, yeah. And
Yeah.
exactly. And if you just look at the case in which you don't get a smaller graph, right? So what will be the case in which you don't get a smaller graph? It will be when this is 0,
Yeah. Empty set.
right? And this is empty set means that this is the whole graph, right? And if this is the whole graph, then actually this will be the whole, then this will actually also be the whole graph. This is all the vertices V, then this will also be all the vertices V, which is easy to see, right? If starting from any vertex you can reach T, then you can reach T infinitely often,
Yeah.
right? That's an easy thing.
Because any vertex goes with it.
Yeah, means yeah, there is a way to reach T, right? From any vertex. May not be in one step, or actually you are right. Yeah. No, yeah, you may not reach in one step, but still you can reach. It means you can reach T infinitely often from any vertex. Okay, so that is fine. So this is basically, and this is important. So when the size of the graph does not reduce, it means that you can end the algorithm there, right? That will be important in the smaller cases to know when to stop.
Okay.
That's
Yeah.
the
Now
point.
I see where this is going.
Yeah. So it's yeah. So it's important in that way. So you do that. So at any point, if it doesn't reduce, then you know that that's what you have to return. Okay. Now let us come to another small thing is that, so these are the vertices from which player one has a strategy to reach T infinitely often, starting from the graph G prime. Okay. So we have to show, right? One has to still show that this is equal to win-win, because this played on a different graph, right? So if it's equal, well, we know mostly it is, because that's how we have got our algorithm. That's how we deleted the vertices we deleted. But still one has to sit and show that this is equal. Okay. So like if anything is in this, then it is certainly in this. That is easier to see. Okay. But you have to also see the converse. So yeah, this one you have to just sit and work out, right? That if V is in this, then you have to show that V is in this. And if you just show this at this stage, then always this will be preserved. When you do G double prime, then also the winning set of that will be winning set of this, and which will be winning set of G of the game played on G. So you have to show this invariance of winning set. Okay. So yeah. So you try to show both the directions. Okay, that if V is in win1 RRG prime, then it is in this. And if it is in this, then also you have to show that you actually don't lose it while going to the smaller graph, which is also what we have already done. But yeah, yes, we have already done all that, but you have to still check it. You have to still show it. Otherwise, you don't know. Right? With all these two, it will be done. So this is sort of it's in a way very ingenious algorithm, right? It's like a different. In the end, it looks easy, but the idea is very different from what you may have seen and things you have seen earlier. So, right. So it's, yeah. Okay. So that is it. Yeah, that is it. This is all that this is. Hmm.
Yeah, and we know it'll end in finite steps because. So how do we know it'll end in finite steps actually?
So it will, in a way, it will not. But you have, by your rule, it will end, because if the size of the, so if G is equal to G prime at any stage, then
Yes.
you know to end, then you know that's where you should end the game,
Yeah.
right? And if that is not the case, then it means that the size is decreasing, but we are on a finite graph.
Okay. Finite graph. And oh, okay, okay. It can't decrease
Right.
forever. Yeah.
Exactly. So you understand the whole thing. It's a nice
Yes.
thing. So
Yes.
either it stops, which means it does. If it doesn't decrease, then you know that your
You can
game,
stop.
you can stop. And if it keeps decreasing, then it will stop by the nature of the graph. So it's a
Yes. Yes, sir.
a nice, yeah, yeah, yes, yeah. You can, if you want, though I suppose you may not get the time at this point, but if you do get, maybe later on, you can visit this thing, this chapter. So this is a book which I had shared, right? Lectures on game theory for computer scientists.
Yes, sir.
There are many
Yes,
other
sir.
chapters. Obviously, this is a big book. Okay, they have some very state-of-the-art algorithms here. But yeah, this chapter I like. This chapter is nice because it's elementary and yeah. But obviously, reading it may be a little bit of, because there is a lot of technical language. One has to see through it. I have studied this at one point earlier. We had a course on this in CMI, Games on Graphs. So that's how I can. I'm more comfortable with it. But yeah. But okay, why did I come here? Yeah, because this is the algorithm, repeated reachability. This is the algorithm, and they actually guide you to the proof, because they don't motivate the algorithm. They just write the algorithm. But the motivation for the algorithm will come if you do the exercises. But I try to do the opposite kind of. Okay, because I'm instructing. So yeah. But if you solve these exercises, then also you will get the motivation for why it was. Yeah. And then there is parity games, which is slightly different. And this becomes very interesting. But you see, the algorithm gets more and more tricky. So yeah, this we will not do. This you can do later. And yeah, maybe you can, if you're reading later someday, you can also start presenting to me and so on. But yeah, that will be for later.
Yes, sir.
Yes,
Yes, sir.
that will be nice, because then that way we can all learn, right? Yeah, as game theory is one topic where you can do a lot without knowing less technical language. Okay. Yeah, so it's something that undergraduates should get into earlier, and it's good. Like the most of the other topics and pure mathematics, they are a little difficult to get to in the beginning. They take time. But game theory is something which, at least this kind of game theory, combinatorial games, one can more easily get started on. Yeah, that's a good thing. So yeah, from art of problem solving book, you can solve problems from games. Also, Arthur Angel has a chapter on games which you can also look at, and obviously it will have great problems. Okay, so you know Arthur Angel's book, right? Problem solving strategies.
Yes, I've heard of it.
You have heard of it? So
I think I've actually, yeah, I've
yeah,
downloaded a PDF of
you
it
would have it.
actually.
Yeah.
Yeah.
You can even get it anywhere in the library, or I think it's a very popular book. Okay, and even some like
Yes.
cheap Indian edition is also available. It's a good book to have, okay? Because it's a sort of a distraction-free thing, because it's a book, and also it's a great collection of
Yes.
problems. And there is a
Yeah.
chapter on
Yes,
games.
sir.
Yeah, there's a chapter on games in that book, which you can look at. At least the first 15 problems you can do. You can try. After that, maybe it gets very involved. But yeah. Actually, those will be harder
Yeah.
because there will not be any theory, and you have to solve all of it by your ingeniousness, most of it. But there will be some principles also.
Okay.
Yeah. Okay then.
Yeah.
So yeah, and do it when
Oh,
mostly
sir,
we, yeah.
and that recursion that you gave last class, I solved it, but I was able to solve it only for polynomials. Like I don't know the general solution.
Okay, so let's do that one. Yeah. That was n square, right?
Yes, sir.
Right. That was.